So guten Tag. Let's get started. And I'm developing a live streaming app. And there are various live streaming apps around the world. For example, YouTube Live, Instagram Live, and TikTok Live, and so on. And if you were to develop a live streaming app, and how would you develop it? Building a live streaming app involves many considerations, especially how to implement the streaming and the viewing functionalities, and minimizing the latency from streaming to viewing, and placing numerous functionalities on the screen, such as the chat and the buzzer gift, polls, video filters, and collaborative streaming, and so on. And having many functionalities means placing numerous components on the screen, and performance tuning, considering all these functionalities, are essential. And today, I'll talk about improvements to our Flutter live streaming application. Especially, I'll cover how we built a live streaming app with Flutter, and what challenges we faced, and how we improved them. So let's start the talk, the Flutter journey of building a live streaming app with a side of performance tuning. And I'll share these slides afterwards, so please don't worry about taking a note during the session. And my English is not very good, so please excuse me if I make mistakes. And if anything sounds strange, and brave my English, not my service. And I quickly introduce myself. And I'm Yugo Sugiyama, but you can call me Sugi. And this is my icon, taiyaki, a fish-shaped Japanese traditional sweet. And I'm currently working at the DNA. And I've been an iOS engineer since 2018, and a Flutter engineer since 2023. And it means since I joined this company, and I started developing this live streaming app with Flutter. And I'm from Japan. The photo on the right was taken on the New Year's morning near my hometown's seaside. And on the right side, you can see the Mount Fuji. And after this talk, and if you are interested not only in my talk, but also in Japan itself, and I'd happy to talk more with you. And this is my first time visiting Europe, and this is also my first time giving a talk overseas. And now let's move on the main part of the talk. And first, let me show you a quick overview of our live streaming app, Play by Sports. And then first, let's go over the main functionalities of the live streaming app we are developing. The service is specialized for the sports, and where both the viewers and the streamers can watch the same video, same sports footage together. And this is a core experience of our service. And this app is available for iOS and Android. And this live streaming system is built using the AWS systems. Because considering the development timeline and available resources, it has been difficult to implement everything from scratch on our own. And now, let's take a look at the implementation details. Let's start with the streaming functionality. The first, streaming requires the ability to cast the camera feed from the streamer's device to server, and which is, of course, essential for the live streaming. And next, both the streamer's videos and the game footage need to be delivered to the viewers with almost no latency. And it also needs to support functionalities such as displaying the viewer's comment, and as you can see in this video, displaying animations as a buzzer gift. And to achieve first and second streaming requirements, we mainly use the AWS Chime SDK. The reason we chose the SDK is that by using WebRTC supported by this SDK, it allows us to show both the game footage and the streamer's video with low latency. And it was also cost-effective. And next, I'll explain the viewing functionality of the Play by Sports architecture. For this part, we need to support the playback of both the sports game footage and the streamer's video, and at the same time, keep the latency between streamers and the viewers as low as possible. And if the streamer speaks and the video reaches the viewers 1 minute later, And the real-time communication, including the comment between the streamers and the viewers, become almost impossible. And with the standard video player plugin, playback itself works, but the latency can easily be tens of seconds. In our case, we need to keep the latency we need to keep the latency within just several seconds at most. So to meet first and second requirement, we chose IVS player. It provides strong low latency capabilities, and the pricing was cost effective. And we also already had internal expertise with this service in my company. And this is an overview diagram that shows the basic structure of the service. And look at it from the left. And first, the streamer device needs to the sports game footage. So the game footage is received by the server from the external service via RTMP, and then delivered to the streamer device. At the same time, the streamer is also sending the camera footage to the server. And because the server and the streamer device communicate with a WebRTC, so the communication occurs with almost no latency. It's like the servers and the apps are in the Zoom or Google Meet code together and with screen sharing. Then the server combines the game footage and the streamer's video into a single stream and delivers it to the viewers using HLS. And with this setup, we are able to keep the latency between the streamers and viewers to just several seconds on average. Next, let's take a look at the core of the playback sports live streaming, how the viewing and streaming function works. In this app, streaming and viewing components use a native SDKs on iOS and Android. We use Amazon Chime SDK for streaming and the IVS Player SDK for viewing. And as a result, only native UI components are provided, so we need to display those native UIs inside the Flutter screens. In Flutter, there are two main ways to display native UI, platform view, and the texture widget. Next, let's talk about the platform view and the texture widget. The basic mechanism of the platform view is that it allows embedding native iOS or Android views directly into the Flutter widget tree. And so, for example, a native UI view on iOS or view on Android can be displayed inside the Flutter. And this is the approach used official packages like the WebView Flutter and the Google Maps Flutter. On the other hand, about the texture widget, the mechanism is at the native side. For example, a camera or a video player produce a frame data. And that frame information is passed to the Flutter through a shared texture, and the Flutter is responsible for displaying it inside its own rendering pipeline. So in other words, the texture widget works as a bridge between the Flutter and the native rendering, making it possible to show camera or video footage directly into the Flutter UI. So this approach is used in the packages like the camera and the video player plugin. Now, let's look at how we using the platform view and the texture widget. Because the platform view often causes the UI issues, our basic approach was to use the texture widget as much as possible. Now, for the streaming screen on iOS, I use a texture widget. I use the CV-pixel buffer output from both the Chime SDK player and the camera's AV capture session. On Android, when I tried implementing it with the texture widget, I ran into the serious frame throttling programs. So partly because of our limited experience with Android implementation. So compared to iOS, implementing the video functionalities on Android is more difficult. So I decided to use platform view instead. And for the streaming screen, due to the SDK limitations, we are using the platform view on both iOS and Android. Of course, we encountered many programs on both the viewing and the streaming screen. The first issue was the battery consumption, especially on the streaming screen. where the battery drain was extremely high. And when we checked the battery energy impact in Xcode debug gauge, and it was maxed out at a very high level. So related to that, there was also the issue of the device heat. The device became so hot that in winter it could be almost be used as a hand warmer. So in addition, the app sometimes crashed, and especially on the streaming screen. Because of that, the live streams were occasionally interrupted, so which was a serious operational problem for our service. So we also saw occasional stuttering in the video playback. From the metrics we collected, the root cause was clear. The system was under a very heavy performance load. So next, let's look at how we improve the performance. And finally, I'll talk about the performance optimization, focusing especially on the parts where the native code and Flutters are integrated. First, let's check which metrics we focused on when thinking about the performance. Basically, we focused on the factors that have the greatest impact on user experience. The first is the frame rate. A drop in frame rate directly affects how good the user experience is. So we consider this very important. And this can be easily measured using Flutter's performance overlay. And in our project, we made it possible to toggle the performance overlay from the debug menu, so even non-engineers such as QA team can measure the frame rate. Next, the surface temperature of the device. Measuring this is a part of the standard policy of our internal QA team. So this is important to prevent users from getting the low temperature burns during the long period of use. And the last is the CPU usage. And this is relatively easy to measure and also make it simple to compare before and after tuning. And these metrics are relatively easy to measure in number, but depending on the measuring environment, there can be some margin of error. So it's difficult to get completely accurate number. And these are, there are, of course, many other possible metrics, but considering the team's resources, we focused on these metrics. And here, I'll summarize how we perform the measurement. And the basic tools are the standard ones used on each platform, and the Flutter, iOS, and Android. For Flutter, we use the performance overlay and the dev tools that I mentioned earlier. And for iOS, we use Xcode debug gauge for simple checks and quick measurements, and instrument when we need more detailed profiling. And for Android, we mainly use Android Studio Profiler, especially for measuring the CPU usage. In addition, for measuring the device surface temperature, we use a dedicated thermometer. And the device temperature is measured by our QA team in this way. And they attach the temperature sensors directly to the device to record the values. And we are very grateful to the QA team for carrying out this kind of measurement. But since it puts a heavy workload on them, so we also want to think about how to make the performance measurement process itself more efficient. And I'm sure you've already used the Flutter tools, so I'll skip them. And next, I'll explain the iOS tool. The iOS debug gauge is a functionality built directly into Xcode. And by opening the debug navigator in Xcode, and you can check a variety of information like this. This screenshot is from my personal apps. But as you can see, it allows you to easily monitor CPUs and memories, energy impact, network, and so on. And on the other hand, Instrument is a standalone performance analysis app that you can launch from Xcode. And by using it, you can measure and visualize your app behavior in detail. And you can run many different kinds of profiling, such as a CPU profiler and a time profiler. in our case, and we mainly used the first CPU profiler to measure CPU cycles. In other words, to quantify how much processing load was required for a specific task, and then compare before and after our improvements. And second, the time profiler to find the bottlenecks in the code. And for Android, we use the find CPU hotspot in the Android Studio profiler to the CPU profiling. To be honest, since I originally come from iOS engineering background, I'm not very familiar with Android development or Android Studio itself. So on top of that, the development period was limited, so I couldn't dive very deeply into the Android profiling in this project. And before going into the full-scale improvements, I first listed a few points that seemed like the potential bottlenecks. Looking at the time profiler, and for example, on the streaming screen, it appears that some of the load was related to the texture widget. So based on these findings, and let's move on to what improvements we actually worked on. Now, let's look at the optimization we made for the viewing screen. And the first one is reviewing the ABR settings. ABR, or adaptive bitrate, is a functionality that automatically adjusts the video resolution depending on the device network condition. And this functionality is built in the iOS Player SDK by default, but the maximum resolution had been set to the 1080p. The higher the resolution, the more data traffic and the processing load on the app. So we adjusted it to the level that wouldn't affect the viewing experience. And finally set the upper limit to the 720p. And the second optimization is reviewing the use of the shader mask. In the comment list, shown in the green area of the number 3 of the image on the right, we use the shader mask for visibility. And in the original implementation, create shader was being called every time the widget rebuilt. So since the shader creation is not cheap, and we changed it so that the shader is generated only once, and right after the screen is opened. And next is the streaming screen. And as I explained earlier, and some adjustments like the shader settings are common to both the viewing and the streaming screen. We lower out the resolution and also reduce the frame rate down to the 20 FPS. And especially for the texture widget, the number of the frame per second and the size of the frame, each frame data can greatly increase the load. And so this adjustment has a strong effect in reducing it. And however, at the core, what was really needed was improving the implementation of a platform view and the texture widget. So how should we make improvements? And to be honest, and when it comes to performance improvements, there aren't many direct ways to optimize using the platform view or the texture widgets themselves. And furthermore, the original structure was already complex. So since time available for performance tunings was also limited, so this was a real challenge. This was a real challenge for us. But then I had a breakthrough. What if we just combine the two videos into one? So in other words, what this means is that the main issue comes from the playing back the two separate videos, the game footage and the streamer videos. So on iOS, this means using the two texture widgets, and on Android, the two platform views at the same time. So which puts a heavy load on performance. So if we could combine these into a single frame view in the native side, and the Flutter would only need to handle the one texture widget or one platform view. So in general, using one texture widget or platform view is better than using two from the perspective of performance. So in the real question is, which performs better? using two texture widget or platform views or merging them into one frame or view. And in this project, we solved this by using the Metal on iOS to merge two pixel buffers into one, and on Android by combining the native views and directly into a single view. So, sorry. And the Metal is Apple's low-level GPU framework for parallel computing. The MSL Metal shading language is a C++-based language for GPU kernels. And this is used to write the code for Metal. And it provides direct GPU access with minimal overhead. And Flutter's UI rendering on iOS also uses this Metal. And as you can see from this table, Metal gave us better real-time performance than core graphics and CI image, so we chose Metal. And from here, I briefly introduce the implementation architecture, specifically the video composing pipeline. And as input, we take two CV pixel buffers, one for the game footage and one for the streamer video. And finally output a single composite frame. The idea is to show the game footage as a main 60:9 aspect ratio frame, and with the streamer video placed below it. And we applied several optimizations, like reducing the resources and reducing overhead. And the details are very technical in iOS native region. So the key point is simply that we streamlined both memory and GPU processing. So let me share how we actually implemented this. So honestly, the Metal offers high performance. It's a very low-level API that's quite difficult to implement. So that's why we leverage these AI tools to proceed this implementation. First, we wrote clear specification in advance. Now we created the test cases before coding and clearly documented with clearly documented and what behaviors to verify. For example, we explicitly defined how game and streamer frame size, the position, and aspect ratios should behave in each case. Next, AI generated MSL shader code from these specifications. And I focused on the correctness over the optimization, leaving GPU-specific syntax to AI. Finally, I did verification and performance tuning. I provided feedback to AI to refine the implementation. The key insight is we don't necessarily need to be a Metal expert. While GPU and Metal knowledge helps, from AI implementation perspective, the clear specifications and implementation logic and the test cases are more important. So loggers are helpful to see what's happening and what values are used. And just a moment. I pressed my mistakes. Just a moment. Okay. Okay, so for performance, it's hard to be perfect from the start. So what matters is meeting the specifications. So step-by-step improvements were more efficient for our schedules. And let me share the result of our iOS implementation using Metal briefly. For successes, we achieved significant performance improvements. I measured CPU cycles per second with the CPU profiler. The image in the slide is a capture of the CPU profiler when I measured. And it went down from about 4.74 gigacycles per second to around 0.91 gigacycles per second. A small difference by environment, but the improvement trend is clear. And details will be summarized in the overall summary. And however, we also face the problems. And our biggest concern is the maintenance cost and the technical debt. And while the current implementation works well, but maintaining and extending the metal code requires either the deep GPU expertise or continued dependence on AI tools. So in our project, the performance issue was critical and needed to be resolved quickly. And so we proceeded with this metal implementation. But please carefully consider the trade-offs. And in some cases, you might need to consider implementing in iOS native instead. And here, I'll briefly introduce Android implementation. And our approach was to stack the player views vertically and merge them into a single view. And specifically, we used the constraint layout. Since constraint layout is similar to auto layout on iOS, I think iOS engineers can easily imagine how it works. And the benefit on this method is that by combining everything into a single platform view, we can improve the performance and also reduce the risk of the bugs. Next, I'll talk about Android platform view. There are three types of the platform view in Android: the virtual display and hybrid composition, and the texture layer hybrid composition. While texture layer hybrid composition is the latest approach, but it is not always the best choice. And appropriate method must be selected depending on the implementation. I won't go into the detail of how each works, but as you can see from the cons, there are performance issues and rendering layout bugs, which made it a real struggle to decide which one to use. And now I'll talk about the issues we faced when updating the platform view implementation on Android. The first one is a Z-index program of texture layer hybrid composition. We encountered bugs where a video rendered with the platform views, which should have been in the backmost layer, was incorrectly displayed in the frontmost layer. And as a result, all the Flutter UI elements, such as the button and the comment list, were hidden behind the platform view. This is a known issue that can occur when the platform view shows Android native surface view. And we resolved this problem by switching to the hybrid composition. Oh, sorry. Just a moment. Okay. And the next is widget ghosting issues that occurred with hybrid composition. On Android 13 and below, after closing overlay screen, a part of it remained as a ghost, as shown in the screenshot on the right. After displaying another screen as an overlay on the streaming screen and then closing it, the part of that closed screen remained on the platform view like a ghost image. And bugs on the specific OS version and our devices are the most troublesome for mobile app engineers, and also for me. And originally, this problem could occur on all versions, but it was improved with the hybrid composition update in Flutter version 3.2020.0. So, however, this fix only applied to Android 14 and above. And so the issue still occurred on Android 13 and below. So since the root cause was the use of the surface view, so we resolved it we resolved it on 13 and below by switching to the texture view-based player provided by the Chime SDK. Although texture view raised the concern about the performance degradation, the proportion of users affected was so small, so we decided to make this compromise. And finally, let's summarize the result of our performance improvements. The device heating issue was improved, and that graph is from the QA team's stress test, showing the device surface temperature over time while streaming. The left is the before the fix, and the right is the after. And before the fix, the device temperature sometimes exceeded 40 degrees Celsius, but after the fix, it stayed in the middle 30 degrees Celsius. The report of the crash and the video stuttering have almost disappeared, and in actual production streaming session, an app crash that interrupted streaming have dramatically decreased. We don't have exact data on battery consumption, but user feedback about it has decreased compared to before. But energy impact still shows very high, so further optimization is needed. So not only from users, but also from project members and QA team, I received a positive feedback. So overall, I think the result can be considered as a success. And we improved the performance, but there are still areas that need adjustment. For example, the energy impact remains very high, which means that there is still room for further optimization. To address this, we need to better understanding Flutter's rendering pipeline and native UI mechanisms such as the platform view and the texture widget. Then this will help us identify the remaining bottlenecks. And of course, a deeper understanding of performance measurement is also important. To be honest, I'll be running these tools myself, and using them more effectively would require quite a lot of learning. I also want to try automating and labor-saving performance measurement. Since the application has many functionalities, I want to add a debug function to switch features on or off, and making it easier to test their performance. This approach allows us to isolate how much resource each functionality consumes and continue driving the further improvements. And due to time, I'll skip this part, but I've summarized the UI implementation for viewing and streaming screens using the custom multi-child layout. And if you are interested, please check the slide later. And I have previously talked about creating a complicated UI like this using a custom multi-child layout. And if you are interested, please check it out from the URL in this slide. So let's wrap up today's talk. So developing a live streaming app requires considering the many different factors, and it always comes with many challenges. And with Flutter, integrating iOS and Android native SDKs make it even harder. And that's why a strong mindset and commitment are essential, not just to build the app, but also keep maintaining it and over time. And this implementation is on our own approach, but we believe there may be better solutions over there. And this Fluttercon is a valuable opportunity to learn, need engineers, and growth, both for me and for this app. And if you have better ideas to improve our app, please share them with me. And I'll give you a small Japanese souvenirs later as a thank you. And these are the references of this talk. And thanks a lot for listening to my talk today. And okay. And you can see this slide from a QR code. And if you have any questions, feel free to talk me individually after this session.